I am David Timmons from the University of Massachusetts in Boston, and my co-author is Rob Turwell from Calavaste in the Netherlands. Our question is about how aviation might become carbon neutral. We started this project before the pandemic and discussed whether to continue given the pressures that airlines are under now. But we decided that this is relevant, that air travel will probably be rethought in various ways anyway. And one of the ways in which we need to rethink aviation is how to make it consistent with limiting climate change. So it seems like a relevant topic for the moment that we're in. While aviation only accounts for about 3% of global greenhouse gas emissions, it's a particularly difficult decarbonization problem compared to other sectors. So our questions are, what are the options, and especially how expensive are they likely to be? What are the economics of decarbonization? In the literature, we find 5 paths discussed for carbon neutral air travel. One is to use battery-powered electric planes, similar to battery cars. A second one is to make synthetic kerosene from biomass that closely resembles current jet fuel. A third one is to keep using fossil kerosene, but to remove the CO2 someplace else and put it in the ground to sequester it. A fourth one is to use hydrogen as a fuel, and a fifth one is to make synthetic kerosene with carbon monoxide and H2, both of which could be made from renewable electricity. In this study, we don't consider battery planes. We don't find much evidence that these are likely to take the place of aviation in the long haul routes, which are the places where aviation is most critical, in the transatlantic routes, for example. And we don't include biomass because biomass is the easiest solution for every energy problem. It's the most similar to fossil fuels that we use now, but there just isn't enough of it. And so it's hard to conclude that this is an option without also looking at all the other things that biomass might be used for. So in this study, we consider only the final 3 options on the list. For the first path, airplanes would continue to emit CO2 as usual, just into the atmosphere. And then at some convenient spot on Earth, the CO2 would be recaptured, liquefied, and pumped into underground geologic structures. If renewable electricity were used for the direct air capture and sequestration, this could, in principle, become a carbon neutral path. A problem with this pathway is that it's not completely sustainable. The kerosene fossil fuel is, of course, a finite resource, so that would be used up over time. And the places where we might sequester carbon dioxide underground are also finite. So that's another resource that eventually would be used. And the more difficult places to sequester carbon would probably be more expensive than we have estimated here. There are also some questions about CO2 leakage from underground reservoirs, whether this actually contains the carbon dioxide forever or simply for a period of time. And there's some other pollution problems associated with both creating the jet fuel and the emissions from the aircraft. So it's not a perfect solution, but it would be better than what we have now. The second path is to use renewable electricity to make hydrogen from water, which could be used directly as an airline fuel. A number of studies have been done on this path in terms of the density of the hydrogen fuel, the weight of fuel tanks that would be needed to contain liquid hydrogen on an airplane, and so forth. And it seems clear that this is a feasible pathway. A problem is that there are, to our knowledge, no examples today of hydrogen-fueled planes, which means that we're probably decades away from being able to actually implement this on a wide scale, given how long it takes to develop new aircraft designs, test them for safety, and all those sorts of things. So this seems like a long-term option, but it's clearly not an immediate one. The third path is the most complicated one and the one that we spent the most time on. The attraction of making kerosene with the Fischer-Tropsch process is that it would very closely resemble current jet fuel, so that aircraft and aircraft engines would not necessarily need to be greatly modified to use it. In order to make synthetic kerosene, CO2 would be captured from the atmosphere. It would then be converted to carbon monoxide, CO, in electrolysis. Hydrogen would similarly be split from water in electrolysis, and then the CO and the H2 get combined in the Fischer-Tropsch process to make the kerosene. Each of those four processes requires energy to do it, which of course would come from renewable electricity in a fully renewable carbon-free system. There are no problems that we're aware of with this particular path, except that it's complicated and, as you'll see, it's rather expensive. But from a sustainability perspective, this path seems to be the best one. The synthetic kerosene portion of this study builds on a previous study by Calavasta of synthetic kerosene for aviation in the Netherlands based on a specific scenario there. Others have demonstrated the technical feasibility of the paths that we're considering in this study, so our main objective is to estimate the costs of aviation decarbonization. What we're presenting is our best estimate of what costs for these technologies might look like 10 years from now. So there's a large degree of uncertainty about costs, of course. There are three types of costs that we consider: energy from a renewable source, sources like solar and wind, which are variable and which affects costs, which I'll talk about in the next slide; capital costs for the investment in the facilities to produce the fuels; and operating costs. Most of the costs are energy and capital. The operating costs are fairly small. In most parts of the world, a renewable energy grid would include a large amount of energy from wind and solar, which are variable sources. This graph shows the cost of obtaining energy in the conditions that prevail on different days. So on windy days, it's relatively inexpensive to get wind energy, and the reverse. If there's not much wind, the cost of obtaining wind energy in those conditions would be relatively high. The graph is from Mauritius, which is a tropical island that's relatively windy and sunny. And you can see that even in these good conditions, there's a tremendous amount of variability. And this results in costs that vary significantly over time. Under some circumstances, it's very expensive to deliver renewable energy, and in others not. In other conditions, the energy is quite available and therefore quite inexpensive. In this study, we reflect this cost of renewable energy variability by presenting costs in three different scenarios. In the first scenario, we assume that a plant only runs 5,000 hours a year, 5,000 out of the 8,760 hours that are in a year. And given that a plant doesn't need to run all the time, if it can be a larger plant that requires more capital investment, but only run in conditions when the electricity is relatively available, then it can probably secure a low cost for the electricity that it uses. So scenario one, the plant only runs 5,000 hours and gets a price of 4 euro cents per kilowatt hour. In scenario two, we assume somewhat more operation, which results in a higher cost for the electricity because the plant requires electricity in more conditions, some of which will be expensive to deliver the electricity. And in the third scenario, we assume almost continuous operation, 8,000 hours a year, with the highest estimate for electricity costs. In addition, we consider three different discount rates for capital for the value that we assign to making the capital investment. And that results in a matrix of 9 different cost estimates for this kerosene jet fuel. As I mentioned before, in these scenarios, there's a trade-off. In order to get the lower cost of electricity, it requires more capital investment, a larger plant size in order to produce the same amount of energy in fewer hours per year. Whereas if we have a plant that operates almost continuously, the plant can be smaller, the capital costs are lower, and the electricity rate is higher. So this is a complex problem, and you can imagine that actual results would vary depending on the circumstances of a particular plant. The highlighted box, 1,709 euros per metric ton of fuel, is what we consider our best estimate. I should say there's also some potential for additional cost reduction through storing some of the gases that are used in the process, but we have not included that possibility here. Here's how the costs break down in the 4 stages of the synthetic kerosene production shown before. The energy costs are mostly in the electrolysis of hydrogen and of carbon dioxide converting to carbon monoxide. This makes sense given that we're just converting energy from one form to another. There's also a little bit of energy cost in the Fischer-Tropsch process and in the direct air capture. The capital costs, on the other hand, are reversed. Most of the capital cost is in the Fischer-Tropsch equipment and the direct air capture equipment, with very little in the hydrogen and carbon monoxide production. So this suggests that there's some possibility for using gas storage, allowing some parts of the plant to run continuously, like the Fischer-Tropsch process, which has expensive equipment, and running the hydrogen electrolysis, for example, only when inexpensive electricity is available, and storing the hydrogen. And in fact, we have some models that look at that, but it gets more complicated. So here we've just assumed no storage and a certain number of hours a year with a certain kilowatt hour price. Comparing the renewable kerosene option to the existing fossil kerosene option and the other two paths that we considered here, you can see that renewable kerosene is the most expensive of the three paths that we consider, 2.9 times more than the existing cost of fossil kerosene. Fossil kerosene plus sequestering the CO2 elsewhere is not quite twice as expensive as the only using the kerosene that we do now. And the hydrogen fuel itself, not counting the cost of a hydrogen airplane, but the fuel itself is the least expensive of the three paths that we considered to replace fossil kerosene. Is this economically feasible is a question based on data that we have on the US domestic air travel price structure. The renewable kerosene option would increase the cost of travel by about 36%. So if you look on the bottom line, fossil kerosene now, we have an average domestic airfare of about $369. That would increase to $500. With renewable kerosene, it would increase to $427 with sequestration of fossil kerosene emissions, and to $403 with hydrogen fuel, again, including only the fuel. I conclude that these prices are economically feasible just because we've seen them before. As shown in the graph at the top, there's a long-term downward trend in the cost of US airfare. To reach the cost that we predict with renewable kerosene, you have to go back to 1993. So you have to go back a while, but it's not the distant past, and society functioned, the economy functioned when airlines had costs at that level. So again, I would conclude that this is economically feasible. Whether it's politically feasible is another question. It certainly represents additional costs beyond what it costs to operate with fossil fuel, but then the fossil fuel path doesn't address the climate change problem. Given the cost difference between hydrogen fuel and renewable kerosene, our calculations based on cost of aircraft for the airlines is that the airlines could spend up to 285% more on hydrogen fueled aircraft. If the alternative were that they had to use renewable kerosene, it seems that it would be less expensive to develop hydrogen aircraft. We assume that for that amount of cost difference, that airlines could in fact afford to develop hydrogen aircraft in the long term. So we conclude that airline decarbonization is both technically and economically feasible through any of the paths that we looked at. The least expensive path is continuing to use fossil kerosene with sequestration of the CO2 emissions, although that has some other questions about the sustainability of that practice. In the longer term, if hydrogen-fueled aircraft could be developed, that does appear to be the least expensive option. But there are also some questions about what the whole transportation system would look like. As you can see from our previous graphs, we would be using renewable electricity in order to make the hydrogen that would then be burned in a jet engine. And the renewable electricity could be used directly to run an electric train or to run an electric car. There may also be some advantages of trains and cars in a post-COVID environment where people want more fresh air, people want more space between themselves. These are conditions that we find on trains and cars that we don't find in planes. So there's several things that perhaps point to a rethinking of the transportation system in general if it were to be based on renewable energy and if it were to be carbon neutral. Here are our email addresses. We would greatly appreciate any comments or questions that you might have. The paper is still in draft form, so revisions can be incorporated. Thanks for your attention.